Welcome to This Explainer. Today, we're totally cracking open the black box of computer vision to figure out how machines actually see the world. Traditional artificial neural networks taught computers how to learn, but it was convolutional neural networks, or CNNs, that really taught them to see. So if you've ever wondered how a self-driving car manages to spot a pedestrian, or how your phone unlocks by recognizing your face in a split second, you are absolutely in the right place. Okay, let's jump right into our roadmap for today. We're going to cover why artificial networks failed images, convolution, filters and features, shrinking data with pooling layers, building visual understanding layer by layer, the complete CNN pipeline, and finally, GoogLeNet, AlexNet, and the deep learning revolution. Let's get to it.
Starting off with part 1, why traditional artificial networks failed images. Researchers were asking themselves this exact question back when their early networks were really struggling. Traditional neural networks worked beautifully for predicting house prices or forecasting stock trends. But when you asked them to identify a tumor in a medical scan, or track an athlete's biomechanics from a video, or even spot wildfire smoke from a satellite, well, the performance was pretty disappointing. Because a computer doesn't actually look at a picture and see a dog or smoke, it just sees a massive grid of numbers. So why did standard networks fail so hard at making sense of those grids?
Think about it like a giant jigsaw puzzle. Traditional networks expect a flat, one-dimensional list of numbers. So to feed an image into a traditional ANN, you literally have to take that 2D grid of pixels and flatten it out into one incredibly long line. It's like taking a beautifully completed 1,000-piece jigsaw puzzle, throwing all those pieces into a bag, shaking it up, and asking someone to figure out the picture. The whole concept of above, below, left, and right just instantly disappears. Plus, the parameter count completely explodes. Flattening just a modest 244 by 244 color image into a single layer of 1,000 neurons requires over 150 million trainable weights. It's just wild and highly inefficient. Which brings us to part 2, convolution, filters, and features. To solve this catastrophic flattening problem, engineers had to get creative. Here's the real game changer. A CNN doesn't actually try to memorize every single pixel. Instead, it uses tiny sliding filters to hunt for specific patterns. Think about when you meet a friend in a crowded room. You don't analyze every single pixel of their face at once, right? You look for local features, the curve of their smile, or the specific shape of their eyes. Well, a CNN does the exact same thing, using a filter, which is sometimes called a kernel. Instead of learning millions of independent weights, a CNN might use a tiny 3x3 filter, literally just 9 numbers, and share those exact same 9 numbers across the entire image. We call this parameter sharing, and it drops the computational cost dramatically.
Picture a document scanner smoothly moving across a page. The filter scans small regions one by one. It starts up in the corner, multiplies its own numbers by the image's underlying pixel values, sums them all up, and spits out a single number. Then, it just slides over and repeats the whole process. This creates a brand new matrix called a feature map. Honestly, think of a feature map like a highly specialized detector. If you're scanning a crowd specifically looking for a red shirt, that red shirt pops out in your vision, right? Similarly, if a filter is designed to find horizontal edges, the resulting feature map will light up with large mathematical values exactly where those horizontal edges live in the image.
Moving right along to part 3, shrinking data with pooling layers. Because even with those clever filters, processing high-resolution images still generates way too much data.
Now, before we start shrinking things down, we got to decide how our filters actually move. Think of stride as your walking speed. It determines how much detail you skip over. A stride of 1 means moving pixel by pixel. You capture every tiny detail, but it takes a ton of computing power. A stride of 2 skips pixels, making the output smaller and way faster to process. Meanwhile, padding acts kind of like a picture frame, giving the filter room to analyze those tricky border pixels. By adding a border of zeros around the original image, we make sure the filter doesn't miss crucial details hiding at the very edge of the frame, like, say, the very start of a wildfire smoke plume in a satellite photo. Once we've got those feature maps, we use something called a pooling layer to shrink their height and width. Max pooling looks at a small window, say a 2x2 grid, and simply grabs the absolute highest number, throwing the rest away. It's exactly like a regional track and field tournament where only the fastest runner from the heat advances to nationals. This dramatically shrinks our data while preserving the most vital pattern activations. Plus, it gives us this cool thing called translation invariance. That basically means if a cat moves slightly to the left in a photo, the pooled feature remains exactly the same. The network still knows it's a cat. Okay, part 4, building visual understanding, layer by layer. Let's see how this steps up from basic lines to recognizing complex objects.
This is where it gets really cool. It's honestly just like building a Lego castle. The network progressively combines simple edges into shapes and shapes into complex concepts like a face or an animal. The first layers of a CNN learn very low-level features. We're talking simple vertical and horizontal lines. As we move deeper into the network, its receptive field grows. So the second layer combines those lines to find corners and curves. The third layer combines curves to find shapes, like wheels on a car or eyes on a face. By the final layers, the network is assembling these high-level object parts into complete, abstract representations. And the craziest part? Nobody explicitly programmed the CNN to look for an eye or a tire. The network discovers this hierarchical structure entirely on its own through training.
Part 5. The complete CNN pipeline. Time to put all these puzzle pieces together.
So let's trace exactly how an image flows from just raw pixels all the way through feature extraction and finally into a fully connected layer to make an intelligent prediction. The image enters and hits a convolution layer to pull out features. We immediately apply a ReLU activation function. Now ReLU just turns any negative numbers to 0, which adds the nonlinearity we absolutely need to learn messy, complex real-world patterns. Then we pool the data to shrink it, and we repeat this cycle. Convolution, ReLU, pooling, over and over, digging deeper into higher-level features. Only at the very end, once the spatial data is super rich with high-level meaning, do we finally flatten the maps into a 1D vector. We feed that vector into a traditional dense or fully connected layer, which tallies up all the evidence, like whiskers, fur, pointed ears, and spits out the final prediction, cat.
And finally, Part 6. GoogLeNet, AlexNet, and the Deep Learning Revolution. Let's look at the historical showdown that actually brought all this theory into the real world.
Let's take a quick look back at how we got here. Before deep learning, humans literally had to handcraft visual rules using complex algorithms. Then, in 1998, Jan LeCun introduced LeNet 5 to read handwritten postal codes. It successfully proved that a network could actually learn its own features using convolution and subsampling. But the hardware back then was weak and the datasets were way too small. The true explosion? That happened in 2012 at the ImageNet competition, where an algorithm was tasked with classifying 1 million images into 1,000 different, highly complex categories.
But the real, mind-blowing leap forward was the sheer scale of it all. By leveraging GPUs and 60 million parameters, AlexNet crushed the competition and proved CNNs could handle real-world, high-res color images. AlexNet took LeNet's foundational pipeline and just supercharged it. It used GPUs to handle massive parallel math. It used ReLU for faster training and introduced dropout, which randomly deactivates neurons during training so the network doesn't overfit. It essentially forces the network to act like a robust team instead of relying on a single expert neuron. AlexNet achieved an error rate of just 15.3%, beating the traditional handcrafted competition by over 10 percentage points. I mean, it was an absolute earthquake in the computer vision community.
There's a great saying in the field. LeNet proved that convolutional networks could work, but AlexNet proved that they could change the world. Because of the foundations laid by LeNet and the sheer scale proven by AlexNet, we now have automated tumor detection in medical scans, real-time pose estimation for athletes, and self-driving cars navigating complex city streets. The simple, elegant idea of sliding a small filter across an image quite literally changed our technological landscape forever.
So, I want to leave you with this final thought. If CNNs have already taught machines to see with such incredible precision, effectively mastering the architecture of human sight, what boundaries of human perception will AI cross next? Thank you so much for joining me for this explainer, and definitely keep questioning what's possible.